All right, so now we're going to talk about the flat structure, what is called E flat and the M flat structure. So the idea is really quite simple, right? It's like when you have a single coordinate chart, you can think of the coordinate chart as essentially being like the Euclidean space, right? And in Euclidean space, it's like there's a very well understood notion of straight lines between 2 points, which is obtained by just taking the convex combination it's like between of those 2 points. Okay, so essentially then what's going to happen in this context is that we're going to do something similar, right? There are 2 coordinate charts. It's like which, if you introduce, there's the primal coordinate chart and then there's the dual coordinate chart. And it's like in each of those coordinate charts is going to define for you some notion of flatness, it's like, and straightness, okay? And we're just going to use that. So the manifold M of the exponential families is dually flat. So the primal affine coordinates are the natural parameters in the exponential family. What I'd call theta, right? In the exponential family. So if I want to have a straight line connecting 2 probability distributions, so I'm going to consider what I'm going to call an e-geodesic. Connecting 2 probability distributions, px theta 1 and px theta 2. So in the theta coordinate system, right, you have that theta as a function of time t is 1 minus t times theta 1 plus t times theta 2. So you know that at time t equals to 0, it starts at theta 1, and at time t equals to 1, it ends up in theta 2, right? Don't need the parentheses. Okay. So then the associated probability distributions, then the associated probability distribution is just the probability distribution associated with that coordinate. Okay, so p of x comma theta of t is just p of x, theta is 0, right? Which is the exponential of t times theta 2 minus theta 1 dot x plus theta 1 times x minus psi of t. Okay. Maybe I should write this as psi of theta of t. Right. So the geodesic itself is a 1-parameter exponential family. Where t is the natural parameter. Okay, so you can think of this as being some sort of linear interpolant in some logarithmic scale, right? So it is the linear interpolant in the logarithmic scale. Okay. And then it's like, since this is an exponential family, as I said, we call this an e-geodesic, right? Where, as you might expect, it's like the E stands for exponential family, or exponential. Yeah. Okay. So more generally speaking, it's like if you have a submanifold in this bigger manifold M, where if you were to write it in coordinates, right, that submanifold has coordinates which satisfy some sort of linear subspace condition, then we call that E flat. Okay. So let's see what I mean. So more generally, a submanifold which is defined by just linear constraints on the coordinates is said to be E flat. And then the affine parameter theta is called the E affine parameter. Okay. All right, so that's sort of the primal part. As you expect, there is a corresponding notion of everything we've talked about so far in terms of the dual coordinate systems. And as you might expect just from the title, it's like of the section, it's like that dual coordinate system is obviously associated with the mixture family. Okay, and with respect to the dual affine coordinates, it's like there's some notion that's like of M geodesics and M flat. Okay, so we're going to talk about that. So the dual affine coordinates eta, and define a dual flat structure. So the dual geodesic, as you might expect, or M geodesic, connecting two distributions with coordinates eta 1 and 2, is given by as follows, right? So again, eta as a function of parameter t, it's just this convex combination. It's like of the two coordinates, eta 1 and eta 2, right? And then as before, it's like when t is equal to 0, you have eta 1, and then when t is equal to 1, you have eta 2, okay? Okay, so, and again, along a dual geodesic, right? happens is that the expectation is linearly interpolated. Okay, so the expectation of x, right, is 1 minus t, the expectation at eta 1 of x plus t times the expectation at eta 2 of x. Okay, and then for discrete probability distributions, right, you have that the probability distribution, it's like connecting, it's like P1 and P2, is really just the mixture, the convex mixture, if you will. It's like those probability distributions. Okay. All right. So, so in this case, it's like the geodesic is along a mixture. It's like of the two probability distributions, and so we call this dual geodesic and M geodesic. So in this case, the dual geodesic is a mixture of two probability distributions. So we call it M geodesic. Where M obviously stands for mixture, right? Okay, and then the same way that you say that a submanifold is E-flat, right? When it's like the submanifold is defined, it's like by linear constraints, it's like on the sort of the primal coordinate system. Here's something similar, right? We see something is M-flat if it is, or a submanifold is M-flat if it is defined, it's like by a linear constraint in this dual affine coordinate system. So a submanifold which is defined by linear constraints in eta is M-flat. Okay. So I should say that one needs to be a little bit careful. It's like about sort of this terminology, right? So in general, so if you're not working with the discrete distributions, you're working with some sort of exponential family, the M geodesic, it's a connecting two probability distributions, right, is not really a mixture. Okay, it's all right. So all right. So I should say the following. So the submanifold. Okay, so the linear mixture, I should say. 1 minus t times p x eta 1 plus t. So this is a convex combination of two probability distributions, right? It's not included in M in general. Okay. So, so what you do instead is to do something like a nonlinear mixture, if you will. Okay, and the way you get around that, right, is to interpolate the coordinates. Okay, as you might expect. So you have p, it's like you have x, it's like, and then you have this eta coordinate system, and instead of taking this naive linear mixture, it's like of the two probability distributions, you take the linear interpolant, it's like between the two coordinates, right? So you do this 1 minus t eta 1 plus t eta 2, right? So this is in M. And we refer to this nonlinear mixture as a M geodesic, even in this case. Okay, so yeah, so the idea of referring to this is like as a mixture family and sort of, you know, mixture geodesics, so to speak, right? Makes sense. It's like in the context of discrete distributions, but for more general distributions, it may or may not be totally true. But nevertheless, it's like you can do the interpolation at the level of the coordinates, right, to give you some notion of a straight line joining 2 points on the manifold. Okay, so let me just stop here for now. It's like, and then the next thing we'll talk about is to try to extend the kind of intuition we had. It's like with discrete distributions, and imagine what happens if you now have continuous random variables instead of discrete random variables. Okay, so let me just stop here for now.